So the structure of the talk will be, first of all, I'll give an introduction, and then having explained how we get to quarks and gluons, which are currently what we work with, I'll talk about the origins of CERN, and then go straight from there to the current projects at the Large Hadron Collider, and in particular, the one that I've been involved in, the Alice experiment. I'll also show how this is connected to the interest from the Catholic Church through the visit of Pope John Paul II to CERN, where I was present, along with a lot of very large number of other people, and I'll then sort of end with some conclusions. So to start with, the idea that the physical world around us might be made of sort of tiny building blocks isn't at all new. It was first mentioned by the Greek philosopher Democritus, who suggested that the tiny building blocks of matter might be very small objects, but he thought that they would be of the same kind as the large objects which we see around us. In the 18th century, Locke sort of came to the idea that that might not be true, that the basic objects might not have all the properties that the objects in our normal experience have. So they may have primary qualities such as position, mass or weight or something like that, but they may not have all the secondary qualities which we're used to, such as color or taste or things like that. So that was a kind of advance over the original idea of Democritus. In 1808, John Dalton, having seen that in chemistry a large number of pure substances had been found, which were being separated into things which are considered as elements, he suggested these might be made of a very large number of identical small particles called atoms, and that then other things, chemical compounds, could be made by sticking these things together in some way. And he noticed that they always seemed to go together in fixed proportions of weight, which suggested that, it gave some evidence in favor of this kind of idea. A little bit later, there was this idea that these elements could be arranged into patterns, was proposed by the Russian chemist Mendeleev in 1869. And he noticed and made into the beginnings of the periodic table the idea that elements that could be put into groups, and things that were in the same groups tended to have very similar chemical properties. That suggests that there was some underlying structure which is giving rise to all this periodicity. It was not known at that stage how that might be, and it turned out that it actually comes from the electron clouds that surround the atomic nuclei in atoms. So moving on, at the end of the 19th century, the very first of the fundamental particles was identified by J.J. Thomson. And not all that long afterwards, the structure of atoms was made a lot clearer through the discovery of the atomic nucleus in 1911, which was found by Rutherford and his very talented group of students. They found that if you take particles from a radioactive decay and fire them at a gold foil, a very large number of times, or a surprising number of times, it bounces straight back, suggesting that somewhere inside the gold foil there was something which was quite heavy compared to the radioactive projectiles, and it was hitting that and coming back. So by looking at the scattering patterns, they were able to work out the size of the objects and things like this. And from that, they came up with the idea of the atomic nucleus. And so from this very rapid number of experimental discoveries, a picture was developed which stimulated and grew up more or less alongside the development of quantum mechanics, which gave physicists the tools that they needed to describe what they saw. You can't really describe the atomic nucleus very well just in terms of the physical tools available in the 19th century. But their nuclei, it was found, have their own regularities, and they can be classified in a similar way to what Mendeleev did for the periodic table. It's a more complicated picture. This thing here is a kind of shows you, it's a little picture of the whole of the chart of the nuclides, which shows all the different possibilities for nuclei. You can't possibly read it, but I magnified a little bit here, so you can see all the different isotopes that can occur for different atoms, which indicate the different ways in which an atomic nucleus can be made up. So, so shortly after that, it became possible for to work out that the nucleus was made up of both protons and other particles called neutrons. And from that, so from those three particles, protons, neutrons, and electrons, it's possible to describe all the structures we see around us. And the next thing that came shortly after the war, when physicists wanted to see what was happening with cosmic rays, which they were aware came into the Earth's atmosphere from outer space. So they applied, they sort of put photographic emulsions up into balloons and flew them up into the upper atmosphere, where they could try and see what happens. And this picture was it was the first time that a decay showing something other than a proton, neutron, or electron was found. It was, so in this picture, you can see this particle coming down, and here something happens. It then decays to produce another particle which goes along in this direction. So what they were seeing, but the people involved, by the way, were a group from the University of Bristol, led by Cecil Powell and Giuseppe Occhialini, was a particle, a pion, that came from outer space, basically, and then it hit something in the emulsion, and then from this a muon was produced, and then this thing then carried on in the photographic emulsion. And in order to conserve momentum, there should have been another particle coming out, which they couldn't see, and they didn't know what it was at that time, but it turned out to be a thing called a neutrino. So from this, and other things done with cosmic rays, it became clear that there were quite a number of new particles in addition to the protons, neutrons, and electrons, which were available. But the technique of using cosmic rays was a bit frustrating because there aren't that many of them around. So in order to get the numbers of collisions and decays that they wanted in order to understand what was going on, they really needed to look for something else. But this this early stage, it was even then very exciting that that all these other types of particles beyond the things that make up our everyday matter were available. So Powell, writing about it, about all these new types of particles, said it was as if we had broken into a walled orchard where protected trees had flourished and all kinds of exotic fruits had ripened in great profusion. So this was discovering all these other types of particles that nobody had dreamed existed. So by 10 years later, by the end of the 50s or into the early 60s, there were hundreds of these particles that had been discovered, and it also became clear they were governed by very strange rules that needed to be understood and were originally written down empirically until then gradually people tried to make sense of them. So in order to try and do this in a more efficient way, you needed a more copious source of these high energy particles and was available with cosmic rays. And that's why there was a need for dedicated laboratories with accelerators. Before we leave this, I'm just going to show you a picture to show sort of how these strange rules work. This actually was taken later with an accelerator. So in this, you have some particles which start at the bottom and go up this way. This one hits a hydrogen atom. This is in a tank of liquid hydrogen, and then various particles come out. In particular, one of them, which goes slightly backwards, is a pion, the same kind of particle that Powell and Occhialini found. And here it moves round in a magnetic field, which makes it turn in more or less a circle, but it's slowing down, so it's not a perfect circle. It then decays into a muon here, and then it decays again into another particle, which in this case is not an electron, but an anti-electron, so a particle of antimatter. So this shows, again, the great breadth of different types of particles that were being found using these types of technique. And as I mentioned, they could be put into systematic patterns, again, with using the same sorts of ideas that were originally done for the periodic table. And from this, it was worked out that they seem to be being made of a smaller number of more fundamental particles, which were the quarks. So they were arranged into families, and each of these had a particular quark content, which might have the quarks. When these quarks you see here are called up, down, and strange, and each one of these different types of particles has a different sort of arrangement of these different quarks inside it, which gives it different properties. So now let's move to CERN and see how CERN came into this. So the origins of CERN came from a series of meetings which were actually originally held in Paris, hence and it was from a group that were called the Conseil Européen pour la Recherche Nucléaire, which was set up in 1952 to discuss how to do these types of experiments and this type of physics. It is, by the way, one of the very first post-war European organizations. There had been a thing called the Iron and Steel Trade Confederation, which was a bit older, but this was really done at a time when there wasn't very much going on. It was quite an important step towards pooling of resources between different countries, and it was brought about because it was realized that basically all ambitious projects in physics at the time were being set up in the United States, and at that time the US had budgets which were well beyond the reach of any one country in Europe. So the only way that European countries might be able to produce something which was in any way competitive with what the Americans were able to do was to look for a joint approach. It was difficult because the different countries were not used to collaborating with each other in this way. And that was one of the main motivations for choosing Geneva, because Switzerland, by its recent history, was known for neutrality, and that was part of the motivation for it being the site for a new world-class laboratory. And it was actually started sort of here in just outside the village of Meran, which is just outside Geneva. It's now, well, Meran is now part of Geneva, and it was quite an innovation, because the idea of working in collaborations was something which, while it's now taken for granted in large scientific projects, was completely unknown in the 1950s, and people treated it with suspicion. Here's a map that shows you basically how the thing works. So this is the village of Meran here. This is the River Rhone. Here is the CERN laboratory. And as it happens, as you'll see, there's another, this is the border between Switzerland and France. Saint-Genis is another village on the other side, on the French side. And there is a second part of CERN, all in France, at a place called Prévesin here. So then it started, and things were brought in from all over Europe to start to build the laboratory, since not everything by any manner of means was done in Geneva itself. However, Geneva also had the advantage that for precision work, it was good, because there were a number of firms which were experienced in precision engineering, basically because of the long history of the watchmaking industry, which meant that the very delicate things that needed to be made for CERN could be done because there were people around who knew how to do it. It's also quite a good site in terms of accessibility from many different countries in Europe. So it was not too difficult to bring things in, as, for example, with this magnet that you see being brought through the village of Meran to be put into the into one of the early projects. And as I mentioned, from the very beginning, CERN attracted physicists from many different countries who learned how to work together, which took a few years. But once the rules of collaborative work were done, it meant that remarkably ambitious projects could be undertaken and were done successfully. That if we now fast forward to the more present day in the Large Hadron Collider, instead of bringing things in just from other countries in Europe, at the LHC we received manufactured components from all over the world, which gives CERN its claim to be a world laboratory and also a world-class laboratory. So CERN builds on its past. So the first of the CERN accelerators was inaugurated in 1959, the proton synchrotron, and then the second one in 1976, which was considerably bigger, and it was fed by particles which had already been accelerated in the first one and went into the second one. So when you got to the Large Hadron Collider in 2008, the whole complex was used again in order to feed the Large Hadron Collider with particles which had already gone through 2 stages of acceleration and were ready to be put into this last stage. And the idea of being able to do that was a big part of why CERN was built on, because it's a lot of the infrastructure was already there in order to build these things. So what about the Large Hadron Collider? Just to recap, by the time we get to the Large Hadron Collider, it was more or less worked out that the fundamental particles seemed not to be the pions and so on that Powell and Occhialini had found, but quarks, and they were seen, and these are the names of the quarks: up, down, top, down, strange, bottom, which could be arranged again into families, again sort of reminiscent of the periodic table, with associated particles like electrons, muons, and so forth, which seem to fit in with these different groups. I'm not going to discuss in too much detail what that actually means. There was another group of particles different from those, which are the things that provide the interactions between these quarks, and so there are photons which do electromagnetic things, but electric fields, magnetic fields, and so forth. Gluons, which bind the things together through a thing called the strong interaction, and these other ones which do a different type of interaction known as the weak interaction. And then finally, as everyone has probably heard these days, there's also the Higgs boson, which is the thing that changes these things from, in principle, being massless particles to having a certain amount of mass. However, for the moment, as far as we know, there's no underlying structure to quarks, to these building blocks here. That's we believe at the moment, the fundamental particles. There's no evidence to go any further than that. So just to remind you, so the light particles are the up, down, and particles and their associated electron and electron neutrino, and these things are very light compared to a proton. That's the proportion of a proton mass that they have, and nevertheless everything around us. So I mentioned the protons, neutrons, and electrons describe everything we see. So therefore, up, down, and quarks and electrons do that. The whole periodic table and everything in chemistry and so forth is made up of these 4 particles. But there are other ones. So in addition to that, you get these other 2 heavier versions with different new things, rather like the electron and the electron neutrino, and 2 extra quarks in that family, and then sort of more quarks in an even heavier family. You'll notice there seems to be a gap here, something that's missing. That corresponds to the so-called top quark, which took a long time to discover, but is very massive even compared with any of the other particles we've described so far. And those are the fundamental blocks. So what are the aims of the LHC era? Well, the things that we want to do are basically, as for the reason that the LHC was built from the point of view of CERN is, first of all, to understand the origin of mass, why particles are heavy at all. And that is to do with the studies of the Higgs boson. To understand the difference, the sort of imbalance between matter and antimatter. It was found that matter and antimatter exist, and whenever you try and create it in the laboratory, you produce equal amounts of matter and antimatter. And yet, if we look around ourselves, we find that there's plenty of matter and hardly any antimatter. So how is that? We have to try and understand where all the antimatter went and how and how we ended up with the universe, which has the structure it actually has. It also, from cosmological models, it appears that something else is needed in order to understand the movement of galaxies. And the candidates for this is something called dark matter, which pulls things through gravity, but doesn't seem to have very many other properties. And it is hoped that nevertheless it does interact in some way with matter, and it would be possible to detect it, if you like, through interactions of the very large number of particles which it produced at the Large Hadron Collider. And then finally, we also want to understand what happens if you go to extreme conditions of temperature and pressure, and with matter of this kind, quarks and gluons, in order to understand what is called the phase diagram of the universe. So just to remind or explain a little bit what that means, when we talk about phases, normally we understand, for example, with water, that it has a solid phase, with ice, a liquid phase, water, and a gaseous phase, which is steam. If you go to very high temperatures or extreme pressures, you can find other phases which are normally not seen, which can also be produced using the quarks and gluons. But those are things that could have happened in the very early stages of the universe, but are quite difficult to produce under any other circumstances. But with the Large Hadron Collider, it's possible to produce similar sorts of conditions. So let's look at what actually happens. So the accelerator ring consists of a series of sort of two tubes which exist in a 27-kilometer tunnel, which goes under both Switzerland and France across the border, and in certain points collides. There are 4 collision points. And so the experimental apparatuses are like this. They're opposite each other. There are 2 ones called Atlas and CMS, which are large experiments which are done for general properties of proton-proton collisions. Alice, the one I'm working on, which specializes, of course, measures proton-proton, it specializes in heavy ions, and another one called LHCb, which specializes in looking at these heavier quarks that I mentioned, the charm and beauty quarks, and studies their properties. The reason for that being that they are the ones where there's the most exaggerated difference between matter and antimatter. Here's a map that shows again the size of this thing. So you can see here on this slightly larger scale, here's the beginnings of Geneva. Here is the village of Meyrin and Saint-Genis, which I showed you earlier. That's the original part of CERN. This thing here is the 1976 superproton synchrotron. And then this much larger ring is the Large Hadron Collider. To give an idea of the scale, this thing here is the main runway at Geneva Airport, which is 5 kilometers. So you can see from that the overall size of the Large Hadron Collider. So I don't want to talk too much about the detectors, but they all have a similar structure, that in the middle of them you have a point where the collisions take place, and around them you have a series of layers of detectors, all doing different jobs in order to detect particles in different ways. So first of all, you can measure one of the particles of the kind like the pion or the kaon, and then later on he was trying to stop the particles in layers of lead and so forth here, and this detects a different type of particle from the one that we started off with. So this layered structure has turned out to be the way that it's most efficient to do these detectors. And again, in this picture you can see there's a sort of typical human scale here to show you roughly the size. Here you have the one I've been working on, the Alice detector. This one, since it works with particles in which a huge number of new particles are produced in each collision, and therefore the main detector, differently from the one I showed you before, is basically empty. It's a gaseous detector, and you just you use ionization to see the tracks inside the gaseous volume. And then outside there are other detectors more like the ones that you saw before. So the idea of it is that you can measure where all the tracks go, and at the same time you can identify each of them to try and work out whether it is, for example, one of the Paolo-Chiellini pions, or whether it's a different type of particle called a kaon, etc. So from this we identify the particles and we find out what their momenta are. So now I'll speak a little bit more about the Alice experiment. So first of all, I want to emphasize that it's big. So here's a picture taken down in the tunnel, 54 meters under the ground, showing just before the start of Alice in 2008, showing a small fraction of the collaboration. And behind you, you can see, behind us here, we can see a part of the detector. That doesn't fully give the idea of it. So here's a much more newer one from this summer. This is a picture taken at just before a meal which was done to celebrate the end of the pandemic, when everybody was able to come back to CERN. Here you have, again, a group of people from the collaboration, by no means everybody. In this one, I'm actually in this one, I'm here, but this thing shows you a life-size picture of the detector, showing the size of it compared to, you know, the group of people here. It's very big. And this shows you the overall number of people. So this was from, I took from the Alice website today. So according to this, there are 2,037 members currently in 40 different countries, which are the ones marked in blue, and 172 different institutes, mainly universities, but also some research institutes. So that gives you an idea of the overall scale and how difficult it is to coordinate the activities that go on in each of the different institutes, so as to be able to do physics in an efficient way. And those are the collisions. That's just one collision between two lead nuclei. And here you can see all the particles coming out. And as I said, from this we were able to identify each one of these tracks, and we're able to tell what kind of particle it is. So the main purpose of Alice, as I said, is to study collisions between of this type, which are actually done not with protons, but with lead nuclei. The reason is that from that you produce a little volume, which is a little bit bigger than with protons, which produces these much higher numbers of particles when the things collide. And the interesting thing is, when this happens, you start with a tiny volume of a very, very hot fluid, which has changed, as I mentioned, into a different phase, into the quark-gluon plasma phase, which until very recently was sort of unknown. This thing expands very quickly and then cools as it does so. It starts at a temperature which is sort of way beyond anything that we've been able to experience before. It's 2 times 10 to the 12 degrees, or if you like, 250,000 times hotter than the center of the sun. And the expansion that comes out is believed to be similar to the type of expansion that might have occurred in the early universe. So people can learn a little bit about how what would have happened under such circumstances by looking at our conditions. And for this reason, because we do it with this tiny little volume, it's actually sometimes referred to as the little bang. I can give you a picture here. So in this simulation you'll see here, you'll see 2 lead nuclei. This is, they are kind of flattened because they are traveling at relativistic velocities. So you end up having what's called sort of Lorentz sort of flattening between them. But in this simulation, you'll see what happens. So if the particles come together at more or less the speed of light, they collide and fly apart. And then in the region between, because of the fields that are created, a little volume, with a huge number of particles is produced, which swirls around like a fluid and then very rapidly expands, cools. And these things here, which are currently at the level of quarks, eventually become the particles that you saw in the picture that I showed you before. When I say eventually, what we've just seen is supposed to take place in 10 to the minus 23 seconds, a very short time, and the whole collision takes place more or less on that kind of time scale. So a very, very short period of time, but one which, through these simulations, we can imagine what actually happens in some detail. So so what we've actually done is that I wrote over the last 10 years, the Alice collaboration has published about 360 papers. I actually looked it up and I'm wrong. It's 13 years since we started. But anyway, it's about 360 papers in scientific journals. And this has helped us to understand what the quark-gluon plasma is, how the quarks and gluons interact in it, and also, and all these things with the quarks and gluons tell us about one of the forces of nature, the strong interaction. And it also allows us to learn a few other things as well. So, okay, this is a picture which often comes up that shows that the laws that govern our particles can be written down in a very succinct equation, which you see here. And actually, for the part that we're describing involving the strong interaction, it just involves these first two terms. These other things describe different types of physics that we don't address. So that's basically what we do. And in so doing, we also, because of the huge number of particles that are produced, we can also learn about other things. We produce the heaviest known nuclei of antimatter. We produce antihelium particles, which have never been seen before, but show that the expectation that antimatter and matter behave in a similar way seems to hold true. So, okay, so that's what this says here. And so now to finish, I'd like to sort of say, why is this of interest to the Catholic Church, and who thinks so? Well, Pope John Paul II did think so. And 40 years ago, on June the 15th, 1982, when he was in Geneva for other reasons, he made a point of visiting us. And as it happened, although the visit was not announced until quite late, I was lucky enough to be there, so I am somewhere in this crowd. I seem to remember somewhere towards the back. He visited a few of these CERN installations. He had, I understand from our Polish colleagues, that when he was Archbishop of Krakow, he often had discussions with particle physicists in Krakow, and it was a subject he was very interested in. So in his address, which is written in this document, which CERN summarized afterwards, he gave us great encouragement in what we did. So let me just read this little bit. He said, "Let me dwell for a moment on the specific nature of the research in which you're engaged. It aims to explore in increasing detail the basic structure of matter, which may be called the infinitely small at the frontier of what can be quantified in the microcosm: atoms, electrons, nuclei, protons and neutrons, quarks. In short, you're attempting to decipher the secrets of matter, its composition, its fundamental energy. That is why not only all scientists, but also all thinking people who reflect on these problems, and it may be said all mankind, are interested or at least concerned. It is, after all, part of their own mystery that is being revealed." Now, these words gave us, as I said, made us feel very encouraged in what we were doing. So to come to the conclusions, the study of fundamental interactions helps us to understand the created universe and to appreciate its complexity. And from these very succinct equations, like the one I showed you, also its simplicity. It's possible to describe it in a very concise way, which shows the beauty of an order in which it has been created. The CERN program has brought together scientists from all over the world in a model of cooperation between nations in order to undertake this task, and we all managed to work well together. The Large Hadron Collider project, which is set to run for many years to come, I mean, people are now discussing what to do in the 2040s, for example, aims to deepen our understanding of specific and rather fundamental questions: why there's matter and antimatter, why there's mass, what holds the universe together, what happens under extreme conditions. And for those of us who work there, the appreciation of these aspects has helped people like me to reinforce their faith. And that's basically what I wanted to tell them.
Dr. Villalobos, one question.
Yes.
Once I was told that in the accelerator, they have managed to make one particle, infinite, to travel at speed faster than light, and that this would have disproven the theory of relativity of Einstein. Is that true or not?
No. It is indeed true. There was there was an experiment which was firing. They wanted to send particles between CERN and an Italian laboratory in Gran Sasso, and they did some measurements which appeared to show that the neutrinos produced in CERN arrived in Gran Sasso at in a time which implied it was slightly faster than light, but they then investigated in more detail, and they discovered there was in fact an error in the way that the timing was done, and that turned out not to be true. It took a long time to actually find the mistake, but there was a mistake in the way that it had been set up. So no.
So the fake news has all the publicity, but when it's disproven, then doesn't have the same publicity.
Well, yes, okay. At the time, lots of people got excited about it. I knew some people who worked on that experiment. They were, to be honest, a little bit embarrassed by it because they weren't sure whether they were they should be able to make such a bold claim. And they spent a long time checking, but they couldn't find what the mistake was for about a year or a year and a half. But eventually they did. They found what it was that had gone wrong.
And what will be the consequence for our faith in creation? The fact that relativity would be proven or disproven?
Well, I think that, I think the relativity as such is just a part of what we can see. And as I said, actually, all the things that we're currently using as our how we as scientists believe that all these things work might still be wrong. After all, 100 years ago, the picture of that we had of physics turned out to be significantly wrong in different ways through the discoveries that were made in the 20th century, and that could happen again. But what is certainly true is that, and can be seen in great detail, is that there is behind it an enormous beautiful order between the things that we can see, and this shows the wonder of creation in a detail that wasn't previously known.
So,
thank you.
One thing I've always wanted to know more about, when it comes to antimatter, like first, I've always wondered exactly how it works. Because it annihilates matter, right? Or like they annihilate each other. So how do we know? Do we know they exist because of how they interact with their identical counterpart? Because my thought was always just like, if they annihilate each other, how do we ever like get to know that their properties?
Well, they in the brief period that the things actually exist. Let me just go back to the picture I showed you of just an anti-electron. So where is it now? Yeah. So here. So this thing existed for a brief period, and you can learn quite a lot about it from the way it interacts. You can learn what its mass is, how long it how it interacts with the matter around it, and so on. And you can see from this that it behaves in exactly the same way as an electron, but it has the opposite charge, and it produces other particles which are different. Now, the idea that, so you might say, well, why is that antimatter? Well, the answer is because you can produce electrons and these other particles, positrons, together from something which is neither. So they you can produce them in pairs, which produces a sort of particle-antiparticle pair. And this is, so normally you think about the annihilation, but actually it's the creation of the particle-antiparticle pair, which is a more interesting thing. When they collide in matter, because after all, they're surrounded by matter, then eventually they get swallowed up and kind of disappear and go back to typically photons. So that, but that part we don't see so much. But in types of experiments, although you can of course design experiments in such a way as actually to focus on them, but from our point of view, in these sort of pictures, the interesting thing is to actually see the particles being created, and you can then learn from the way they interact with matter and from measuring their momenta, their various things like that, whether their properties are the same as the corresponding particle. They should be, and in all the things that have been done so far, that appears to be the case. And so yeah, go on. Yeah.
So things like charge. So it'd be just like the electron would be drawn in one direction, and they notice the positron goes in the opposite direction.
Exactly. Yeah.
Okay.
So, okay, another thing we can do in this picture, which you probably, I didn't point out to you. Yeah, so, okay, so this is this anti-electron, which you can see is curving around in this way in the magnetic field, but you can actually knock out electrons from atoms in the field, and this is what's happening here. So you notice here, this is an electron that was knocked out from an atom, and it curls around in the opposite direction. And that's what's known as a delta ray. But that's you always find these things around, and that tells you what negative particles do, and then you can see what happens with particles that curve in the opposite direction.
Okay.
So Orlando is still with us, if anyone wants to put a question to him.
I have a question which is not scientific. Whenever I heard about antimatter, I was suspicious about, because it gave me the idea that this was a kind of Manichaean way of conceiving the world, where you have matter and antimatter, and so a kind of God of good and God of evil. So, but now I hear you speaking so with such familiarity and friendliness towards antimatter that I want to know why this is not Manichaean.
I think it's just, I mean, antimatter is normal. It's produced all the time, and it is just as much a part of creation as anything else. The only curious thing for us is that, and this is one of the things that we hope to find out, is that although when we create it, you always create equal amounts of matter and antimatter. Nevertheless, if you look around, most of the antimatter has somehow disappeared. And so this is something that we have to understand. Now, it turns out that for certain types of particles, the matter and antimatter are not quite produced equally. So through the interaction that I didn't mention very much, the weak interaction, there are slight differences, and it could be that those gave rise to over a long period to the differences which we see, but nobody really knows. And this is why now we're trying to measure carefully these subtle differences between matter and antimatter in order to see whether they explain why now we live in a world of matter and not with equal quantities of matter and antimatter. I should say that that's good, because if there were equal quantities of matter and antimatter, then we would probably not exist in the way we are. So it's obviously part of God's plan that the antimatter should have by now disappeared.
Yeah, that's very reassuring.
So when it comes to, like, I don't know if you've read Aristotle's physics, would you say then that, like, matter and antimatter would be still both under what he would call matter?
Exactly.
That since they are something that interacts physically with the universe, that even though antimatter and antimatter is more of just a way of naming it because it has this antagonistic reaction with matter, but that they're both part of the physics of the universe. And so they're both, in a sense, matter in the way that Aristotle would see it.
Yes. I mean, the idea that basically the idea of these particles originally came out of the equations that Dirac, who was looking at how this could be described in quantum mechanics in the 1930s, realized that in addition to the solutions to the equations which he was obtaining for looking at matter, that another family of solutions came which appeared to have opposite properties. And he was a bit puzzled by that because at that stage nothing had been found, and it took about another 15 or 20 years before these antiparticles were found. But they're called antiparticles in that sense that they do indeed annihilate with matter if they collide with another particle of the same but opposite sort of thing. But and they're also created together always. So, but in other ways, they are just as much a part of matter as their partners, the particles. So, and for each particle seems to have an equivalent one. So I don't know, protons have antiprotons, neutrons have antineutrons, and so on.
Interesting.
And
may I ask something? I don't know. I don't know
Yes.
if I have to switch on or off something. Apparently, you can hear
No,
me.
no, it's perfect.
Yes.
Okay. First of all, I'm really almost amused, slightly amused to see that the Academy Defending Life is actually interested tonight in dead matter. And I must say, engineer by trade, it's a bit of a wake up call for things that I've looked at a long time ago. I see somebody is interested in the physics of Aristotle, which is greatly stimulating me to ask this question. Because I'm a priest. I'm sorry, because I'm not heating my room. I have something very warm over my habit. But you see that we've all seen this almost tragic development of the school of Teilhard de Chardin, who wanted to unite theology and modern science without passing by the realism of metaphysics and even physics. So it would be great if actually within the academy there could be a sort of a workshop on this. Are you worried in your search for what is reality? Are you in any way worried by some contradictions, like the fact that in one way it's a particle, we're flying through empty space. In another way, the rationalization is a wave, which suggests something is moving on a broader foundation, which still needs to be defined. And in quantum physics, are you in any way embarrassed by the fact that reality exists by chance, except for the one that is observing reality, which is almost making yourself God, Everybody and everything exists by chance, but I have to exist absolutely. If not, the whole system is impossible.
Collapses.
I don't know.
Yeah.
I'm not trying to corner you. I'm just trying to figure out.
Well, I think what you describe is part of our sort of incomplete understanding of how it all works, because the idea with quantum mechanics and that particular interpretation of it is a human description of what is happening. And it helps us as human beings to try to understand it. But it doesn't, in some sense, really imply that is how God sees it, if you see what I mean. That what we are doing is trying to find ways of trying to get our minds around what creation is, which makes us think in terms of this idea of contingency in space, and indeed that matter in some ways is like a wave, in some ways it's like a particle, and so on. But they are there are ways of describing, of us trying to imagine what we're doing. I mean, I've recently read a book that says that, instead of that, we should be thinking that everything we see in quantum mechanics is simply a solution to a partial differential equation, and the idea that we describe it as a wave or a particle is just us not fully managing or trying to find models in our head that can help us to understand it, that in some ways it behaves in one way, in some ways in another. So no, I don't think so. I think it's just because we have to find ways of trying to conceptualize what we see, but it doesn't mean that what we see is forced to be like that.
I've never been bothered by it either, you know. Just
No.
but,
Yeah.
but isn't it in a way the incompleteness of Gödel in its widest sense, which actually was already observed by Aristotle, although in a very primitive way, that we can never fully rationalize reality as such, except by our intelligence in metaphysics, isn't it?
Well, all these things are. I mean, okay. So the idea, the incompleteness of Gödel is one of the things that has been proposed, for example, as a way of getting out of deterministic ways of describing physics, which, by the way, quantum mechanics also does, because from the way that our laws that are written in terms of quantum mechanics work, there are certain things normally on a microscopic scale that we cannot with it predict, which may be our lack of understanding, or it may be that that's actually how that the tiny scale uncertainty is supposed to be. That we simply don't know. But I think it's both of this. So both I think there's a slight difference here, that the quantum mechanics predicts that at some level there is a kind of incompleteness. The Gödel suggests that whenever you try to make a theory, there will be something you can't prove inside it. That's not quite the same thing. So but both of those point in the same direction, that when we try to...
It's an analogy. It's an analogy.
Yeah, when we try to conceptualize, there are things that we miss.
To add something to Professor Villalobos,
Yes.
he said that the last sentence of his conclusion was that all these studies had helped to strengthen his faith.
Yes.
Now, my question is, if he has seen more, if you have seen more scientists becoming theist from being atheist, or the other way around, because of these studies,
I've seen I think what I've seen is this. I haven't seen huge numbers of changes, but I have seen that amongst my colleagues working in this field, there are quite a lot who do practice faith. There are quite a large number of practicing Catholics working in it, and we continue in it, and we strengthened by things like what John Paul II told us, feel that what we are doing is something which helps to understand our particular little aspect, which is to improve our understanding of the wonders of the created universe. So we don't feel that what we do is going to prevent us from or create doubts in our faith, but instead what we do we feel is useful. In fact, I remember even once I was in Geneva, I was told in confession that that was something that was important that I should have to do, to go and try to make sure that people knew more about the created universe from the work that I was doing.
Oh, the church doesn't have a fear of science.
No, exactly. Yeah.
That's for sure. No?
Thank you very much, Doctor, for such a fantastic presentation. Really, I'm stunned by it. But you mentioned dark matter and dark energy.
Yes.
I mean, are these just really to try and fill in the blanks of where, you know, there's gaps in the information, or is there solid evidence that there is such a thing as dark energy and dark matter, or is it just simply?
Well, that's a little bit beyond. That's a little bit outside what I do, but basically the idea is that when you look at on a very, very large scale, so the opposite of what we're doing, which is looking at a very tiny scale in cosmology, we know that how galaxies work, and we know people have quite a good idea of how heavy they are, how far they're moving apart, and so on. And the motion of galaxies doesn't seem consistent with just the gravitational pull that they have on each other. So you can, astronomers or cosmologists can calculate how much they should interact with each other through gravity, how much, one galaxy pulls another. And it doesn't really describe what's being seen, that they, it seems that there's something else which is sort of also acting, which holds them together, which we can't see. So that's basically, so we can either assume that gravity doesn't work, but we don't want to do that, or that it does work, but there's something else which we can't see. And that's the reason why we call it dark matter. It's dark because we can't see it. But the idea why it's interesting for us is that although we haven't seen it yet, it's hoped that in some way it does have some kind of relation or interaction with normal matter. And through all these particles that we produce, we might detect some way in which the dark matter is influencing our particles. So the idea is that maybe dark matter is made of particles and they decay sometimes into normal matter or something like that. Theoretical physicists have various ideas about how this might happen, but nobody really knows. So it's basically one of these things which we are always on the lookout for sort of strange things or unusual things which might indicate that that's what we're actually seeing. That's basically the nub of it. But it's needed not directly for us. We don't have direct proof of it ourselves, but from cosmology, it's known that something we haven't understood that needs to be we need in order to describe what we are seeing with the large scale motion of galaxies.
And is there anyone who thinks that science might be wrong about gravity and about would that be such a radical proposal that it just nobody wants to even discuss that?
People don't want to, one of these things is that one of the things that happens is you have a kind of inside science where we always say that you can always disprove anything, but nevertheless there's a kind of what's described as a sort of hierarchy of belief inside science as to which things you're most likely to want to abandon. And you don't really, people want to try to stick to the idea that we're basically right with gravity and look for ways to describe it before exploring too much the idea that gravity itself, our current description of gravity is just wrong. I mean, some people are thinking about it, but the majority, but not very many. Most people think that it's, that there should be something there that explains it all inside the picture of gravity that includes gravity.
Well, thank you. Thanks. That's helpful.
I have actually a couple of different questions, but I don't want to take up too much time. I guess first off, so there's a couple of things I was thinking about once again with the matter antimatter. Would this be equivalent to the idea of, you always hear the famous E = mc squared, that there's something about the property of the matter that it turns into energy? Is that what happens? Because we say annihilate, but obviously it doesn't go out of existence, right?
It It converts into it converts into sort of something which doesn't have mass. So, for example, when they annihilate, they know depends on what they are, but normally they would the most likely thing was they would produce photons. Now, the photons have energy, and so you've got back your energy. So the idea, and when you work the other way, you make a collision, and from a certain amount of energy, you produce a sort of matter-antimatter pair.
Okay. And then if I could ask you, I don't know how much you know specifically about gravity, but I've heard a bit about the gravitons, and I've just never fully understood exactly how they function, or like how things can be drawn together when they are, multiple light years apart. It would seem to me that they would have to be like almost, if there is some kind of particle interaction, it's like they're being drawn by particles that were emitted like light years, because like they can't move faster than light, right?
Yeah. Yeah. I think nobody else understands gravitons either, so you're not alone. But
okay.
The main problem with it is that gravity is by far, in a way, the weakest force. It's much, much weaker than anything else. So in terms of what we can study, for example, in the laboratory, we won't see any effects. But the other forces of nature have all been sort of proved to be describable in terms of exchange of these force particles. If I can put back my picture for a second. So I will, so where are we now? That when we, so if I move forward, so when we, here. So these things in the pink column here, they are particles which are exchanged between so these things, if you like, are matter particles, these things here, and these things are exchanged between them. And and when you, for example, have an electric field, they're basically done by exchange. The picture that we have built up is they're done by exchange of photons, a bit like if you throw a sort of beach ball or something between two people in a swimming pool. You can exchange a photon, bounce photons from one side to the other, and so forth. And the result of all that is what in the end produces an electric field, or if with slightly different conditions, a magnetic field. So the different types of interaction which we've dealt with so far, which are strong enough to be seen in a laboratory, can all be described in terms of these particles you see here. So the picture that people have with gravitons is that probably gravity can be described in a similar sort of way. Now, for different reasons, the graviton we can sort of work out some of the things that it ought to have because of the distribution of gravity, which is rather like that of an electric field. It should be a massless particle, and there are a few other things like that, but nobody knows how to actually find one. And because in order to actually find a graviton, you would have to be able to think of some way of detecting it in the same way that in the end people have managed to detect photons and Z bosons and so forth. And the only way we know is if they, by choosing some situation where if they interact with matter, they can excite interaction so that they produce other types of particles. And that in the end is how all of these things have been found. So the Higgs boson normally we don't see it, although it's all around us, but by going to a suitably high energy, you actually get to a situation where a Higgs boson can actually produce new particles, and that's how it was detected. So the same thing, one would hope, could happen with a graviton, but nobody really knows how to do it because nobody really understands how gravity interacts with matter, except through this extraordinarily weak force, the gravitational field. So, so basically, we're stuck at the moment. We don't know how to do it.
And so wait, so I guess that this is something I didn't realize, that gravity and mass aren't the same thing. Because we
well,
always think of mass because of gravity, or
yes.
and it's a function of mass, at least the power of gravity, right?
Well, if you go to gravitons, then the idea is that gravitons are sensitive to mass, and therefore that they interact in such a way that the more mass a particle has, the stronger the gravitational field. But in such a picture, you know, the mass is something different. Now, the picture is also, okay, now moving into more complicated things, which I'm not that familiar with, but the other complication with gravity is that according to Einstein, if you the gravity is related to the curvature of space and time. So it may be that trying to deal with it in terms of gravitons is not an appropriate way to do it, and it actually should be done in a more geometrical way. And the original proposal that you can have exchange particles called gravitons might just be wrong. But as I said, it's something that nobody knows, and nobody even knows how to find out at the moment.
Thank you very much, Doctor.
Well, if no one has any other questions, and I certainly don't, and just a sense of wonder, I'll thank Orlando for his huge amount of effort. He put a great deal of preparation into this very clear talk, and the Academy is very grateful to him. Thank you very much, Orlando.